motivation. All right. Converting back the other way is kind of the same idea, so I'll put a star on that. And the same idea goes for converting into function forms. Very straightforward because, again, cylindrical coordinates and polar coordinates in 3 dimensions are really synonymous. So if I say convert to polar form and I give you 3-dimensional coordinates, it's implied that I'm talking about converting over to cylindrical. All right. If I give you 2-dimensional coordinates, then it's polar, but it's all the same because all cylindrical coordinates are polar coordinates with height, with a height z. All right. So z is going to remain the same. If I want to get into polar form, I need an r and a theta. All right. R is equal to the square root of x squared plus y squared. So square root of 1 plus 9 is going to be the square root of 10. Now the theta, you have lots of possibilities here, but the easiest one to work with is the inverse tangent. So inverse tangent of y over x. So, and again, coordinates are x, y, z. It's still the same x and y from the first unit. So inverse tangent of -3. All right. So you just have to think about whether or not that's a unit circle ratio. And the reality is, it could be or it might not be. In this case, it's not. Radical 3, sure. Radical 3 over 3, 1 over radical 3. Basically, anything involving a radical 3, you're looking at something that's unit circle related. If it's a 1 or a -1, same deal. 0, undefined, same deal. All right, but not the case here. So we are going to get an angle here that's not going to be pretty. All right, and there's nothing wrong with that. So there's a couple of ways we could express our answer. Let me get my calculator. And the couple of ways that you're going to express your answer are really strictly dependent on what you need the information for. All right, so one way to express your answer could be something as simple as saying the square root of 10, comma, the inverse tangent of -3, comma, 5. All right, because that's my r. This would be my theta. And this is my z. This is a pretty flexible way of writing your answer because inverse tangent could be expressed in radian form or degree form, depending on what mode your calculator's in. Right? So, you can't be wrong. If you didn't put units there, you can't be wrong because inverse tangent could be in either form. If you put units, if you put degree, you're right. If you put radians, you're right. All right? So that's good news. I'm going to put my calculator in degree mode and then just hit inverse tangent of -3, see what comes up. We're talking about roughly 72 degrees. All right? So we could say, or root 10. Now the reality is, if I'm going to estimate the angle, I might as well estimate the radical. So about 3.2, so I'll do approximately 3.2, 72 degrees, and 5. All right. Writing it in that form is beneficial if you need to graph it, right? Because visualizing something that's in inverse tangent form is even beyond my ability. All right, so being able to visualize it in degree form and estimate form for radian measures, that's a little bit easier. All right. So, say it again. Sorry. All right. Oh, I did, huh? Oh, look at that. Thank you. Oops. So negative 72 degrees. which actually works out nicely because when I went to plot that, it wasn't going to bear out the way I wanted it. So glad we found it. All right. So looking at this XY plane, right? So it's always going to be a little iffy to visualize this stuff, but the more you try, the more successful things are going to be. So what we're trying to do is estimate where first 72 degrees would be, because the last thing you're really considering is the vertical movement. All right, you want to place it on the XY plane first. All right, so what I would be doing is labeling this as 0 degrees, 90, 180, 270, and then you swing around to 360, right? That's a weird looking 0 degrees, so I'm going to fix that. It's not much better. All right. So what's happening here is we're dialing it back 72 degrees. So that's what this angle is here, 72 degrees in the negative direction. All right. This distance here, that's your approximate 3.2. All right, so what's happening is you're taking 3.2 steps in the direction of negative 72 degrees and then shooting 5 units upward. All right, so visually it's kind of mind-bending to think about that, and in fact, you might even question, oh, well, why would I ever want to do that? Because it's so much easier to plot the points in rectangular form. But as we talked about last class, in a lot of cases, it's a whole lot easier to differentiate and anti-differentiate when it's in polar form. All right, so that's what we want to do here. All right, and we also want to be able to think about different surfaces that might have cylindrical equations. So in the case of r squared plus z squared, well, we know r squared is the same as x squared plus y squared. All right, so x squared plus y squared plus z squared is equal to 9. What we're looking at there is the equation of a sphere, but we're able to represent it as a function of two variables, r and z. All right, so I can represent z as a function of r, right? Because really, if you're thinking about it, you have 3 variables that come into play when you're dealing with the cylindrical system. You have r, theta, and z. So any of the variables could be expressed in terms of the other variables. You generally don't want to have it expressed as a function of 2 variables. If you can avoid it, you'll settle for that, but you want to try to avoid that, because this way, if you have it as r squared plus z squared equals 9, you have a single input and a corresponding output. All right. Whereas if you have it as x squared plus y squared plus z squared, now you have 2 inputs and 1 output. All right. So it's more convenient to have it in the other form. Now it's even more convenient if you can get rid of, let's say, for example, the z. If we're living on the xy plane, then z equals 0, and now you're just looking at the circle, r equals 3. But what this will do is it'll give us it in the form here. This bad boy right here. This gives us a way of determining the radius of the sphere at any height. All right, so we'll know what the radius is of the sphere at any height z, just based off of that expression. So much more useful from our perspective. And thinking in terms of differentiation, yeah, partial derivatives are fun, but I'd rather just go back to, where possible, go back to a simple dy dx. In this case, dz dr, or dr dz, So that's along the same lines as the second one, where we're representing theta as a constant function. Theta is always equal to pi over 4. Now, when we graphed this back in the first unit, it ended up being a line. But here, it's a little bit of a different story. All right, so we're going to have inverse tangent of y over x is equal to pi over 4. But then we're going to take the tangent of both sides, in which case we get y over x is equal to tangent of pi over 4. Tangent of pi over 4 is equal to 1. And you might say, wait a minute, you just said it's going to be something different. You're full of crap. Yeah, you got me. It really is a line. No, it's not a line. We're in 3 dimensions. If it's going to be a line, it would have to be represented parametrically, all right? So when you have something like y equals x, it's y equals x for all z. So this is the equation of a plane. All right, so it's a plane that has an x, y intercept of y equals x. All right, so the part of the plane that intersects with the xy plane is the line y equals x. But it still extends upward and downward forever. All right, it's parallel to the z plane. All right, I'm sorry, actually it's not parallel. It's just, yeah, it's kind of parallel, but it's not really, because it's intersecting through it, so parts of it, I guess, are. Points on it are. Right? But what we're getting at here is that the expressions and equations that we use to define lines in 2 space for polar graphs are now going to be used to express planes in 3 space. All right, but that's pretty consistent with what we've been doing. Then you have the simplest one out of all of them, which is z equals r. You might say, okay, well, waiting for the other shoe to drop on that one, because nothing seems to be what it seems to be. Z squared plus z squared equals 9. Not necessarily. Yeah, because z squared is not the same as x squared plus y squared. So it's not like you could just substitute out this guy here for another z squared, if I'm understanding correctly. But in this case, what you'd actually be doing is squaring both sides to get a relationship. And you'd have z squared is equal to x squared plus y squared. Oh, that's what you're saying? Okay, now I get it. All right. It took a second for it to click. This is a new function that is defined based off z being equal to r. It's not a universal truth. Right? So we're not always going to say that z and r are the same thing. It's just we're looking at the function where z is equal to r. So the part of the graph where z and r values are the same. All right. Now, if you look at this, I mean, this is kind of a solid beast here. You look at it and say, all right, well, I guess z equals plus or minus the square root of x squared plus y squared. And you might look at that and say, I don't know, what is that? You know? You could also look at it as, or x squared plus y squared minus z squared equals 0. Really, no matter how I write this, it's not going to be as clean as z equals r. Right? I mean, that's kind of the moral of the story here, and by kind of, I mean it's definitely. Right? So it's just a question of, okay, well, what is that then? You know, so it's obviously some sort of square root function, because why? There's a square root in it. But what does it look like? So for that, we'll kick over to GeoGebra and take a... Yeah, it's one of those situations, like, honestly, it's actually part of the curriculum for this. I mean, every time I check, I double check to see if my eyesight is like playing tricks on me, because part of the curriculum is exploring these different surfaces in 3-dimensional space, right? And so the ellipsoid, which is a 3-dimensional ellipse, a sphere, a hyperboloid, and a paraboloid. Right? They call them quadric surfaces. Right? So very close to quadratic, but it is basically just a play off of that. Yeah, there's like in the curriculum, there's like weeks that are dedicated to just exploring these things. And then I looked at all the other things that are in the curriculum, and I'm like, you don't have weeks to explore that. You just deal with it as they come up. All right, and the reality is you don't really need to know what a lot of these things look like in order to handle the calculus parts of it, but it does certainly help. If I'm not too much mistaken, I could double check real quick, but I definitely put a bonus tech assignment up on my website, so let me pull that. All right. Typo. My example 1 should be to revisit the example that we just did, the unit sphere question, just using this new approach. So it's just a question of I'm going to do it here or I'm going to do it there. I'll do it over here. Just steal some room. All right, so volume. Oh, hell of a question. 79. We're going to find the volume of, or under, z equals the square root of 1 minus x squared minus y squared. All right. In cylindrical coordinates. So we'll just find the volume of the entire, I'll just do a hemisphere. All right, so the volume under would be between the function and, so between z and xy. All right. So what I want to do is I want to actually convert that over into polar form. All right, so I have a rectangular set of coordinates. I want it to be polar. All right. So I'm going to pull out a negative. Oh, and sorry, polar, cylindrical, interchangeable. So I say polar and cylindrical, and I mean the same thing. All right, because all cylindrical is polar coordinates with height. All right, so if that's a source of confusion, then try not to let it be, because they mean the exact same thing. So minus x squared plus y squared. All right, so a rule for polar coordinates, just so I don't have to flip back and forth, x squared plus y squared is equal to r squared. So I want to define z in terms of r's or thetas, but not in terms of x's and y's. All right, and so after I make this slight adjustment, mission accomplished. 1 minus r squared under the radical. All right, so we won't be able to simplify that any further, so that's where we leave it. All right, but I also needed to know what the bounds were going to be for this. All right, so what we need are r bounds. So we need r bounds and we need theta bounds. So r bounds and theta bounds. So the structure, and I'll just point out the rule here. The way I have the zooming set up, it's not going to be the easiest thing to see, but we're looking at some function of r theta, or function of r comma theta, times r dr d theta, or r d theta dr. Right? So there's an extra r in there, And I'll explain next class where that comes from, because I have a proof here, but I have a better way of explaining it through actual calculus. So I think I just copied this on the internet, but I have a much better way of explaining why there's an extra r there. And it has to do with the concept of a derivative, so we'll talk about that next class. But anyway, so we need r bounds and theta bounds because my variables are r and theta, right? It's just a question of whether it's the r's that are going to come first or second. So we're going to set up our integral so that the r value is going to be addressed first. The r bounds will be addressed first and then the theta bounds, all right? The theta bounds are usually pretty easy because if I'm taking one full turn around a circle, then that's going to be 2 pi radians, right? So we're going to go from 0 to 2 pi unless you're only looking for a portion of a circle, right? But before we even get into that, what I would want to do is figure out the base region on the xy plane. So that part is no different. So what I'm going to do is I'm going to take this function and set it equal to 0 and solve. Now we already did this for the other problem, and we got x squared plus y squared equals 1. All right, we could actually work off of that, but I'm going to pretend that didn't happen, all right? Because it's actually pretty easy to solve it once you convert it over into polar form. Square both sides, you get 0 equals 1 minus r squared, which means r is equal to, well, I'm sorry, r squared is equal to 1, which means r itself is equal to plus or minus 1. All right, now the negative values when it comes to r just imply direction. So the r value that would be -1 is just telling us to take a step away from a given angle, all right? It's going to turn out that we don't need the negative, all right? So we're going to say therefore r is equal to just a 1, and then that's going to define our set of boundaries, all right, for r. Because we're really just working out in the direction of r from the pole, right? So 0 out to r, that's going to populate all of that space that we're looking for. Because in the form of a sketch, we know it's circular base. Oops, elliptical base apparently. Circular base. Circular base. Whatever. I'm just faking it now. All right, good enough. Whatever. I'm just talking about botching it. All right, what we're doing here by stating that r is going to go from 0 to 1 is that we're populating out our area this way now in terms of arcs with radius varying between 0 and 1. And we would do that in every direction, defined by whatever we're allowing theta to be. All right, so I shall just do it all the way around. So infinitely many circles with varying radii in between 0 and 1. All right. So what that means in terms of a double integral is that I'm looking to go from 0 to 2 pi for theta, because I want to go all the way around the whole thing. I want the whole top half of a circle, which has a base region that goes from 0 to 2 pi. All right, it's the entire circle.
So we are looking down.
Correct.
At the region, not sideways.
Not sideways. Yeah. So it's not a profile view; it's a top view. All right. Then I'm going in terms of my r function. Now, this is the beauty of using cylindrical or polar coordinates appropriately. If you're dealing with a circular function, a polar representative of that is going to be very simple. Like x squared plus y squared equals 1 is pretty nasty, all right? But the polar equivalent to that is just r equals 1. If I had another circle, maybe not centered around the pole, you know, something centered around the y-axis, I might have, you know, something really complicated like x squared plus y minus 3 squared equals 25. But when it comes to the polar variation of it, it's really just going to be something times cosine of theta. Something times the sine of theta. right? So very, very simple, all right? So here, my R values are just going from 0 to 1. And I just want to make sure that I'm living underneath the function, the square root of 1 minus R squared times R dr d theta. So this is a much, much simpler expression to work with, all right? I'll clean it up a little bit. In the process of integrating, though, you can see on the interval of 0 to 1, I have R square root of 1 minus R squared dr. It's even in this first step of the double integral, it's calculator friendly, all right? And that happens very often when you have a circular function that you're evaluating using cylindrical coordinates, all right? So math 9, R, so X, root. I mean, you can use U substitution here if you want, but you don't want. I don't want. Nobody wants. Ah, I hit quit. I didn't want to hit quit. Or mode, I mean. So you get 1/3. All right. Now we're integrating that with respect to theta, which, I mean, you do that by hand. 1/3 theta over the interval of 0 to 2 pi, and you get 2 pi over 3. Now, the motivation, I think, is there to learn about cylindrical coordinates, because you looked at what we set up in terms of the integral. I don't think you needed, it was only for half, yeah. So if I wanted the whole sphere, I would just double it. But you could really just imagine having to evaluate that interval on the what, 3 pages earlier, related to really the same problem, but it would take you a page and a half to do it. All right, so much, much quicker and easier. The trade-off is you have to become proficient with your conversions between polar and rectangular form. All right, so what I'm going to do is pop a star, whoever Papa Star is, on number 1 at the bottom. It's really just asking you to evaluate it in polar coordinates. So the integral is already written for you. You just have to convert it over and then evaluate it. So we'll tackle that next class. That should be your motivation. You should look at this and say, I don't want to do that. That's crazy. I'm gonna change it into polar form or cylindrical coordinates and work with it that way, because it's just going to be so much easier, all right? Because this is not even something that your calculator is going to handle with great ease. You know, that's a lot of typing that you'd have to do, all right? So, and that's the best case scenario. That's assuming the calculator could even handle it at all, all right? So we have our z function here. So we're not overly concerned about this just yet. What I'm really more concerned about is the bounds. What I have are 2 sets of bounds, one in the form of y equals, I want to go the other way with that, and one in the form of x equals. So what I'm going to do is I'm just going to make a note. Y equals the square root of 4 minus x squared. And y equals negative the square root of 4 minus x squared. I'm just going to denote that with a plus or minus symbol. Now, if you recognize that as a circle immediately, great. If not, square both sides. Y squared is equal to 4 minus x squared. Add x squared to both sides. X squared plus y squared is equal to 4. All right. So I want to represent that in polar form. Well, we have a relationship that tells us that x squared plus y squared is equal to r squared. So r squared is equal to 4, which means r is equal to 2. All right. It's a circle with radius of 2. Now you might say negative 2, but if the path is generated in all directions 2 units away from the pole, it doesn't matter if you're going forwards or backwards. You got to pick up all those points anyway. All right. So that's that. I mean, we could draw that surface, that cross section in the XY plane. So let me just do that real quick. Get a little circle going on here. Undo. Change the opacity here. That's an ellipse. A little bit better. Okay, I can't erase all of this. Now it's saying that it's going from x equals 0 to x equals 2. Well, here's x equals 0. And here is x equals 2. All right. So if I'm living in that interval, I only want this portion of the graph. So thinking in terms of the theta values, and that would be relative here, or relevant, just threw out a word. We'd be looking at negative pi over 2 to pi over 2. All right. The other possibility would be to say, well, I'll just take whatever's going from 0 to pi over 2 and double it later on. But the problem with that is we don't know what this function looks like, this z function. Because remember, it's hovering in space over this circular region. All right. So you have some wave that's coming through potentially, or maybe just a flat surface or whatever. But we don't know how it's behaving in the area above this circular base, all right? We don't know if it's symmetrical. If it's not symmetrical, then I can't just say I'll take 0 to pi over 2, get that answer and double it, all right? So we have to work with the entire base region, all right, just in case, unless you happen to know something about the function itself. So I now know that my bounds for r are going to go from 0 to 2, because I would be starting here at the pole, and then I would be working my way out in terms of r. But I'm getting restricted based off of the x values so that I can only be living in the interval between negative pi over 2 to pi over 2. All right, so I'm looking at negative pi over 2 to pi over 2. 0 to 2. Now I got to do something about that function. All right, because y squared, x squared. Well, I'm about to write this in terms of r, dr, and d theta. All right, because dy dx is going to be replaced with r, dr, d theta. And I mentioned last class that I'd explained today why that is the way it is. All right, a little proof coming your way in a few minutes. All right, so that's kind of an issue. Well, I do know that y is equal to r times the sine of theta. All right, that's on the previous page, but I'll write it again. X squared plus y squared is equal to r squared. So I could actually write x squared as r cosine theta quantity squared and replace the y squared inside the parentheses with an r sine theta quantity squared. But since I already know it's going to be equal to r squared, I might as well just leave it at that. All right. So we're looking at r sine, oh, poor quality r sine theta squared times, this is going to become r squared to the 3/2. Before we get into the integration process, we want to clean it up, definitely. All right. So r squared sine squared theta times r cubed times r dr d theta. All right, so that cleans further to r to the 6th sine squared theta dr d theta on the interval of 0 to 2, and then on the interval of negative pi over 2 to pi over 2. So now I just have to integrate. But the integration part of the process should not be difficult now. All right, because I'm integrating with respect to r first. So anything that's not an r is going to be treated as constant. So the intimidating part of this, which is the sine squared theta, is irrelevant. That's just going to stay put. I'm going to integrate the r to the 6th. It'll become 1/7 r to the 7th. We still have the sine squared of theta, and that's going to be happening over the interval of 0 to 2. All right, so I just want to clean it up. 2 to the 7th, I think, is 128. 2 to the 5th is 32, then 64, then 128. I think it's 128. 128 over 7 sine squared theta. All right, and so we're going to integrate that over the interval of negative pi over 2 to pi over 2. Now it's a function of one variable, so I could just pop it right into the old calculator. Little math 9 action. So a little fraction, 128 over 7, oh, get out of here, 7, sine, close it up and square it for some reason, x. Now I have my calculator in degree mode, so I'll have to change that, or I could just put negative 90 to 90, but you play with fire when you do that. So I'm gonna type it in and then change my mode. So you get about 28.7. All right, this is a measure of volume, so units cubed. You could just watch. You know, I'm not going to assess you on this, right? Because proofs are tricky on an open notes test. You know, it's like I can ask you to do like 5 proofs, but the reality is you'd just be copying them all out of your notes. So half the test would be stuff that you're copying out of your notes. So I try to limit what I'm going to ask you, and I've already committed to what I'm going to ask you to do. So. All right, so dy dx, all right, is what I'm going to be looking for here. But let me go back to the roots here. So x is equal to r cosine theta, and y is equal to r sine theta. All right, so I eventually need dy times dx, so that's something different, but you got to start somewhere, so this is where we're going to start. All right, so what I'll find here is dx dr, which is going to be, if we're doing it in terms of r, we have to find the derivative of this implicitly. So first times the derivative of the second. If this sounds familiar, it's because we did this already in the first unit, but it's what we're going to do with it that's going to be a little bit different. So first function r times the derivative of the second, which would be cosine of theta times d theta dr, plus the second, which is the cosine, sorry, brain cramp. Fun fact of the day, derivative of cosine is not cosine, negative sine. I was more focused on writing the d theta dr that I forgot to do, you know, basic calculus. All right, so second cosine times the derivative of the first, which is in terms of r just going to 1. All right, so that's one little relationship. The other one would be dy dr. Again, product of two functions. First times the derivative of the second, so cosine theta times d theta dr, plus the second function times the derivative of the first, which gets us to the sine function. All right. So I can multiply through with a dr in both cases and get two new equations. Dx is equal to negative r sine theta dr. I'm sorry, negative r sine theta, because the dr's will cancel out there. D theta plus cosine theta dr. And then the dy, same deal, r cosine theta d theta, because the dr's cancel out, plus sine theta dr. All right. So that could give me my derivative. So this is right back to unit 1, where I would say my derivative is r cosine theta d theta plus sine theta dr minus r sine theta d theta plus plus cosine theta dr. All right, so that's where we've been. That's what the rule was back in the first unit for finding the derivative of y with respect to x. All right, so now what we would have to do is one of two possibilities. And really, it's reliant on this information in one way or another. I have to multiply dy and dx by one another. So whether I do it up here by multiplying both sides by dx squared, or down here by just simply multiplying dy and dx by one another, the act of multiplying them together has to happen. All right, so dy times dx, I'm sorry, dx times dy, it doesn't matter the order, it's commutative. All right, we're not getting into the over a rectangular region. I'm just simply looking for the product of dy and dx. So I'm going to rewrite the top one so it's a little bit more convenient. Cosine theta dr minus r sine theta d theta. That's going to get multiplied by the other bad boy, r cosine theta d theta plus sine theta dr. All right, so I'll have to distribute things out, but that's just algebra. So r cosine squared theta dr d theta. The outer functions, so that's going to be plus sine theta cosine theta dr squared. The inner function, it's got a lot of the same ingredients, you know, the sines and cosines, but it also has an r squared and a d theta squared. All right, so it's not like we can combine them. That would have been nice, but unfortunately not the case. So minus r squared sine theta cosine theta d theta squared. But then the last one is going to be minus, I'll put it over here, r sine squared theta dr d theta. All right. That one seems to have a few ingredients in common, so we could do something with that. All right. I am concerned I made a sign mistake because this is supposed to clean up nicely. First times for the second. Cosine squared dr theta. Good. That one's fine. Yeah, there's nothing wrong with it. I mean, unless there is something, I'm just not seeing it. All right, so I have a common r dr d theta, so I can pull that out. So I'm going to have r dr d theta cosine squared theta minus sine squared theta. Then adding on to that, we have, well, I could pull out a sine theta cosine theta. Everything else is going to pretty much stay put. So we're looking at plus sine theta cosine theta dr squared minus r squared d theta squared. All right, now, yeah, it should still work. I just thought it should go to sine cosine squared plus sine squared. I might be thinking of something else. All right, well, anyway, we're looking at dx dy is equal to all that. All right, now, we just got through working with a bunch of problems where, well, a couple of problems anyway, where dx dy or dy dx was being replaced with an r dr d theta. All right, so just the first part of the green here. So the big question would be, all right, well, that's great. What about all this other stuff? All right, and that's because what's happening is if you're finding an instantaneous change, what we're really looking for is the product of an infinitesimal change in x and an infinitesimal change in y. All right, so this would be happening over a very, very tiny interval. Right? So what we can now do is we can assume that theta has to be approaching 0, because in order for there to be a teeny tiny little interval, that must be the case. All right? So I'd be looking for the limit as theta approaches 0 of dx dy, which would be equal to r dr d theta. If I substitute a 0 in everywhere I have a theta, every instance of sine is going to go to 0, and every instance of cosine is going to go to 1. All right, so out of all of this, we're going to have a 1 squared minus 0 squared plus 0 times a whole lot of other stuff. All right, and so this pairs itself down to r dr d theta. All right, and that's only because we're talking about an infinitesimal change in distance traveled. You know, you just look at a triangle. You know, and that's really where the inspiration for this kind of proof comes from, is that if you talk about a triangular movement, whatever happens to x and y has to also necessarily happen to theta. All right, so I have x and y corresponding with theta, you know, all in all the trigonometric forms. Sine of theta is equal to y over r, tangent of theta is equal to y over x, and so on. So if y is minimizing itself to dy and x is minimizing itself to dx, then theta must be minimizing itself to d theta. All right, and so that ends up being the crux of all of this, right? Or at least the motivation. All right, so like I said, it's definitely not something I'm putting on the test. Besides, it's kind of a lengthy one, and this part of it here is such like an intuitive component that I would hate to just have people writing that down without fully understanding it. I want, you know, a proof that you could produce on a test that you would actually understand, you know. Because we kind of liked it when they gave us the double integral, because then it was just mechanical. You get right to work. I gave the figure here. It definitely looks a lot nicer on the big screen than it does on your paper. It's like a big gray blob. But what we're talking about is like a little capsule contained in it. So we have two different paraboloids intersecting one another. And the intersection forms a bounded region. That's what we're looking for. Right? So what I first would want to do is find the intersection of those surfaces. All right, very easy to do because they're both solved for y in terms of x, solved for z in terms of x and y. So we have x squared plus y squared is equal to 5 minus x squared minus y squared. We can add x squared and y squared to both sides. So 2x squared plus 2y squared is equal to 5. X squared plus y squared would be equal to 5 over 2. All right, so that's a circle, which, you know, like I said, the diagram on your papers aren't much to look at, but in this one here, if we're talking about the intersection, we're talking about the little area here. Yeah, it could be a circle. All right, in that middle region there. All right, we're just talking about the border created by the intersection. All right, now in polar form, that would correspond to r equals the square root of 5 over 2. All right, because, I mean, you could do your substitutions. You can let x squared plus y squared equal to r squared, and then square root both sides. But the bottom line is you're really just finding the radius of your circle, and that ends up being your polar equation. So why not just cut to the chase? All right, so we have that. Our theta value, you know, if I did an xy trace of this, undo. You know, just based off of the diagram there, you know, no matter where I draw my circle, if I draw my circle down here, or up here, or up here, or down here, or down here, no matter where I draw my circle, it's still going to be a circle. And a circle goes from 0 to 2 pi radians. All right, so we have our r and we have our theta. Now we just need some way of representing the function. All right. So just like you would if you were finding the area between two curves, you find the area of the top minus the area of the bottom. I'm sorry, that's what you're looking for. You find the difference between the top function and the bottom function, which gives you the area bounded in between. right? Because you know that you're integrating all of those little rectangles that go from the beginning to the end of the region. You just need the distance between those two functions, all right? So what you want to do here is find the top function, the top surface, and then subtract from it the bottom surface. So I need this guy. All right. So you got two choices. You got z equals x squared plus y squared. I'll write them both down here. And you have z equals 5 minus x squared minus y squared. All right. Now, if you made an educated guess without investigating any further, you'd probably guess correctly. If you're guessing that the function that's facing downward is the 5 minus x squared minus y squared, it's a good guess. It's the right guess. Right? Because you're starting off with something that has a value of 5 and you're only subtracting from it. Right? So that would mean that it has to max out when x and y are both 0 with a value of 5, because that would be the case where you're not subtracting anything from it, which would put it right on the z-axis, which is what's happening here. All right? But maybe you don't see it that way. All right? So if that's the case, one of my buzz phrases, I guess, you might say 5 minus x squared plus y squared in parentheses is the same as 5 minus r squared. All right, so what that's doing is it's creating a relationship between z and r. So as the radius increases, the z value gets smaller and smaller. All right, or that's the equation of a parabola with a negative coefficient, which means it's opening downward. All right, so if you like that, you know, go right on back to algebra 1. You're like, oh, it's a downward facing parabola, because the leading coefficient's negative, right? The other one would be an upward facing parabola, because z would be equal to r squared. All right, but if you can try to conceptualize this, it makes a big difference, because what this is saying, again, is, you know, the r represents the radius, the distance away from the z-axis. As the distance away from the z-axis, as the radius increases, the figure gets moved further and further down the z-axis. All right, so that should naturally create that paraboloid look. All right, and this is the same idea, just in the opposite direction. All right, as the radius increases, it gets further and further up the z-axis. So that's a parabola going in the positive direction. All right, so if you start to try to internalize it that way, it definitely makes more sense. All right, so my double integral going from 0 to 2 pi, then 0 to root 5 over 2 of 5 minus r squared minus r squared, all that times r dr d theta. All right, so then we can clean it up. All right, so this component here, 5 minus 2r squared times r, which in turn becomes 5r minus 2r cubed dr d theta. I like that a lot better, because it's just reverse power rule. That's nothing. Increase the power by 1. Divide by the new exponent. Increase the power by 1. Divide by the new exponent. All right. So this is going from 0 to root 5 over 2. So that's nice. We have even powers. That's the best thing that could happen when you have a square root that you're putting in. So 5 halves times 5 halves minus 1/2 times root 5 over 2 squared becomes 5/2, squared again becomes 25 over 4. Bottom line is, it's not radical anymore, so that's a win. So we're talking 25 over 8, 25 over 4 minus 25 over 8. Which is 25 over 8. So then I'm just dealing with a single integral going from 0 to 2 pi of 25 over 8 d theta. Well, that's just 25 theta over 8 on the interval of 0 to 2 pi. And so that's going to be 50 pi over 8, which would then be 25 pi over 4. I didn't really look at the calculator for this one because the numbers were just working out so nicely that it wasn't even worth getting into, right? But it gets pretty messy. Well, I made it pretty messy because I made this so huge that I robbed myself of space elsewhere. But it's really not that bad one way or the other. Right? And again, once you get to this step here, because really this is all, now honestly, because this is a function of one variable, this is all calculator if you want it. Right? Because you could integrate this because there's no thetas in it. You could integrate this in your calculator, get the answer, and then integrate the result in your calculator. All right, so there's really, once you get the setup, there's really not many ways to screw this up. All right, but I have faith in you. You'll find a way. That was a joke. It was a bad one. All right, we're not finding anything funny tonight. Okay, cool. So I'm going to put a star on the next one. And then we will carry on to the next page. Just had a thought. Because the best way to really kind of get good at this stuff is through experience. So I don't want to do too much of the thinking for you. You'll see some names here. Find the volume, like in number 5, inside the hyperboloid of one sheet. It's like, now we're just making up names for stuff. And that's really what it is. It's just that it's one continuous hyperboloid. It's connected. As opposed to a hyperboloid of 2 sheets, which is 2 separate graphs that together make one function. But you have to actually pick your, well, I was going to say pencil up off the paper, but really like your easel up. I don't know, your paintbrush up, because it's 3-dimensional, so it's always definitely a work of art when you get done with it. But it's connected is really what that's saying. All right. So I'll leave those for you to try, and then we will talk about triple integrals. Now, triple integrals are pretty easy in that, like you don't necessarily realize that you've been using triple integrals all along. Like even for finding like single integrals, you could represent it with a triple integral. All right, double integrals, certainly you could represent it with a triple integral. Right? It's just very often ends up being an extraneous step that's unnecessary, right? But really what we're trying to do here when you're finding a triple integral is you're finding little cubes that exist within a bounded region, all right? The volume of little cubes. So we have a dimension, and this length here would be dx. This one would be dy, and this one would be dz. So what you would end up having is infinitely many. So this is like a Riemann sum in that you have infinitely many teensy tiny little cubes that are occupying this space in this direction. So we would integrate with respect to x. All right, so we have our dx. We would integrate all of those. All right. Then we would have each of these teensy tiny little distances in the direction of y. So each of these every one of those collectively, if you integrate them together, if you combine them all together, would give you the sum total in that direction. And then what you would have is all the teensy tiny little distances in the direction of z. So the vertical distance. And that would give you the triple integral of some function of x, y, z. So the natural question that you might have, because really what we're doing when we take all our z's, you know, we have every one of those, that's just on one level. Honestly, we're going all the way up with this bad boy, but, you know, it becomes kind of a waste of time. Like all of those cubes would be shooting on up the line here until it occupies the entire space. So we'd have one of these for each one of them, and so on. So we would occupy all of the space in each direction. All right, pretty crazy. That's a lot of space to occupy. But you might be wondering, wait a minute, didn't we just find volume? Didn't we just do that with a double integral? So why are we doing it with a triple integral? And the answer is, well, because we were using triple integrals, we were just skipping a step, all right? And I'll show you what that means in a sec, all right? So, well, I'll show you now, but it'll take a sec. So the first example, use a triple integral to find a volume between a surface defined by the function below, there's our function, and the region, so it's a rectangular region in the xy plane, which is fine, all right? So that means that we can swap our x and y bounds all we want. So we have a z function defined in terms of x and y, all right? But what we could do is define this function as f of x, y, z so I could write this as a function of f of x, y, z. I put my arrow the wrong way. Or I could write it as a function of x, y. It all depends on how I want to approach this thing, all right? But let's say we want to keep it simple and focus on writing it as a function of x, y, z, all right? And let's just say, I'm sorry, x, y. And let's just say that that function is unknown. What I would need is a triple integral It doesn't matter what the order of integration is because of Fubini's theorem. All right, if you're over a rectangular region, the order is interchangeable, and that's what's happening here. All right, so I can state that this is going from -1 to 1. This is also going from -1 to 1. All right, so at this point I can say, well, I have, well, what do I have? Some constant? Maybe. What I can do is I can just say that this is some function that we'll call 1. All right, whatever you want. It doesn't make a difference. But what we're going to do is integrate it over the interval of 0 to z. All right, so if I solve this for z, I'd have z equals 4 minus 2x plus y. All right, because really the bottom line is what I need to do is bound this function. And the dz, dy, dx is the function that gives me the volume in that bounded region, depending on what the end of the boundaries of integration are, right? So the fact that I am multiplying these three things, oh, that looks terrible, undo. The fact that I'm multiplying these three things here actually gives me the volume. So infinitesimal volume. That's not how you spell infinitesimal. Crap. I don't think I've ever spelled it. I've always just said it. Infinitesimal, I think. Yeah. Yeah, it's a good thing I didn't have that word in the 4th grade spelling bee championship of Dutchess County. Otherwise, I wouldn't have won. So, volume. By integrating all of those infinitesimal volumes together, I'm getting the true volume bounded by these three boundaries of integration. All right. So, you could carry out the process and say, all right, the antiderivative of 1 with respect to z is z on the interval of 0 to z. Okay, so that's just z. And that's a general rule. So what this ends up being is equivalent to -1 to 1, -1 to 1, z, which in turn is equal to 4 minus 2x plus y, dy dx. All right, so what we're actually doing here is we're actually applying the step prior to the double integral. Because the last problem, what we would do is we would just jump off with this. We would find the double integral for a particular z function, and then with the appropriate boundaries of integration, right, associated with the variables of integration, right? But by showing this additional step, all we're saying is that there is that one component where we're actually generating the z function in and of itself that allows us to apply the double integral concept. All right. So at this point, now you're just applying techniques for finding the solution to a double integral. So I'd be looking at, well, I just focus on this piece. Integrating with respect to y, we're looking at 4y minus 2xy plus 1/2 y squared over the interval of -1 to 1. I'm going to do a little plugging and chugging. All right, we're plugging in for y. So 4 minus 2x plus 1/2 minus -4 plus 2x minus 1/2. So 8 minus 4x, and then that would be plus 1, so 9 minus 4x. And so then it just becomes an ordinary integral. On the interval of -1 to 1, which you could pop in your calculator if you want. Nah, might as well. Undo. Less writing. So 9 minus 4x. I know it's linear, but it's been a long day. So 18. So it actually ends up being a pretty clean answer. So you might be wondering, okay, so could I have figured that out using another method, like maybe a geometric approach? This is the equation of a plane, and planes are usually pretty user-friendly, but the thing is we don't know what kind of plane it is. If it's parallel to the XY plane, in which case it's just a matter of length times width times height, but odds are it's some triangular looking plane, so it's on an angle, right? If that's the case, then you would have some length times width times height, but then you'd have that wedge part of it that you'd have to figure out, all right? So, yeah, it's pretty interesting. Now, it is possible that you could be taking a triple integral over a rectangular region or even a non-rectangular region, but that triple integral is going to give you something called density, right? And that density in here is the same as density that you'd be evaluating in physics class, all right? So it's basically taking the concept and expanding it into the fourth dimension, because the triple integral is finding, like you would think volume, but if you're talking about a fourth dimensional graph, you're talking about each different line or point having a texture to it, or a thickness, or a mass, or a density, all right? So it's really just, it's not a matter so much of occupying space, it's how the space is occupied. So when you get into the fourth dimension, you got to imagine, and this is where things kind of get crazy, because you really do have to imagine it. There's some apps out there that try to do a pretty good job of it, but like we have a space in here. Like I could tell you what the volume of this space is, but at any different location in the space, the temperature is different, right? Maybe in a very minuscule sense. Like maybe it's 72 degrees in one spot and like 71.98 degrees at some other spot. But there is varying temperature. There's variance within this volume, all right? Anytime something varies over a three-dimensional space, that puts it into the fourth dimension. Right? It's very commonplace that people represent the fourth dimension as time. That's a complete fallacy. That's not at all what it is, right? You could represent time as a dimension, but that doesn't necessarily mean it is the fourth dimension, all right? Time could be the 10th dimension. It doesn't make a difference. It's just a dimension. It's not designated as the fourth dimension, right? Because we have a whole lot of other dimensions to get through before you start thinking about what would be time. Like what would be the physical manifestation of time? Because we do have a physical manifestation of density of gases. Like it just like right out of an old Batman TV episode. The air conditioner all of a sudden starts spewing out noxious gas. All right, so the way the gases are diffused within the environment, all right, that would be a new variable within this confined three-dimensional space. How that gas varies in this space is a new variable that puts us into the fourth dimension. All right, so how do you graph that? Well, not easily, right? Because we're already struggling. By we, I mean me. You'll probably do a better job than I would, but graphing something in three dimensions is already a pain in the ass without technology. So imagine doing something with fourth dimensions. So like air currents within the three-dimensional graph. You could see it all the time on weather maps. Like the old school ones, like in elementary school, when you were learning about like jet streams and things like that. All it was like an arrow on a map, but that didn't tell you anything about like where that arrow was relative to the ground, what direction. You get a general sense of the direction, but we didn't get a sense of what the slight minor variations are. All right, so if in order to really represent the fourth dimension, you would have to plot every single particle that could exist in the domain of that three-dimensional space. All right, so if the idea or the word nightmare is coming to mind, then that's the correct word, because drawing that out is just terrible. All right, so if we start getting into things like volume, then the natural next dimension would be something like density, because that's one thing that we could do is we can evaluate the density over a confined space. All right, so we have rho equals m over v, right, and being mass and b being volume. So M is equal to rho times the volume. All right. So if we get a product of rho and the volume, then what we end up doing is creating a triple integral of some new function that density function multiplied by volume. So density so the product of density and volume gives us mass. So the triple integral of density and volume gives us, as a result, the combined mass over a space. All right, so this is equal to the combined mass over a space. And honestly, the only real way to accurately and effectively graph in the fourth dimension would be by using, by hand, would be by using different colors. So areas with the highest mass, you would make that the darkest colors, and the lowest mass you'd make with the the lightest colors. But density. But the issue is you have three different directions to be working with. So how do you do that if it's not uniform in terms of the density down a particular line? All right, so I have a plane here. If the density varies, so I'm looking at a cross section of that plane. If the density varies down that plane, from this perspective, I wouldn't be able to see it. So now I have to ever so slightly shift my perspective so that it's on a little bit of a slant so that I can give it texture all the way down the line. All right, and what if it varies from bottom to top? All right, so density in terms of fluids, for example. If it's not uniform density throughout the fluid, oil and water, right? You take a little Italian dressing, you buy it at the supermarket, it's divided, right? But then you shake it up, now it's all mixed, but it's gonna start separating itself over time, right? So that movement is variable, but the density of the liquids and how they push off of one another, it can be represented with a fourth dimensional graph. All right, not easily. All right, but that's the beginnings of that.